In the last class, we saw that in a nonlinear systems, there can be a large number of possible behaviors which are not possible in linear systems. So, what have we seen? First, we have seen that there can be limit cycles. And in limit cycles, we have seen that there can be various types of limit cycles, like there can be a periodic orbit like this, where I am drawing the axis here. There can be periodic orbit like this also, if the system is 3D. There could be a periodic orbit like that is also possible. And then we have seen that there can also be orbits that cannot be called periodic. The same state never repeats itself. So, in every turn and twist it traverses a new path, and such systems we learned are called chaotic. And yesterday we saw one mechanism of that to happen. What was the mechanism? In the system that we considered in the last class, there were two eigenplanes not parallel to each other, they are intersecting with each other. In one, the rotation, that means the corresponding equilibrium points are unstable, and they have complex conjugate eigenvalues with positive real parts, so that they spiral outwards. But in one, the outward spiraling behavior is clockwise, the other, the outward spiraling behavior is counterclockwise. As a result, as it goes out, it gets thrown into this plane, and as it goes out, it gets thrown into this plane, and as a result of this motion, the whole thing remains bounded. So, that was the mechanism that we learned. There can be various other mechanisms also of producing the phenomenon that we talked about. What is the crux of the phenomenon? One, the orbit is bounded, it does not go to infinity. Two, it has no periodicity, and three, there is sensitive dependence on initial condition. That means, if you start from arbitrarily close initial conditions, then after some time they will move apart. What its physical implications are, I will come to that little later. But first, let us look at another system, just to make ourselves comfortable, because otherwise there is a possibility that we may be led to think that it happens only in that system. So, there are actually a very large number of physical systems in which that happens, but most physical systems, as we have seen, are yield somewhat complicated equations. Here let us deal with somewhat simpler equations, because it is also a point that one is often led to believe that such things happen in very complicated systems. No, not true. Such things actually happen in very simple systems, and that is why it is more logical to consider simple equations to show that even in such systems this kind of phenomenon can happen. Let us take another set of equations called the Rosler equation. This is O with a umlaut, that is a German thing, with pronunciation Rosler. You will make the lips as if you are trying to speak O, but you will actually try to speak A. So, whatever comes out of your mouth, that is the O. Okay. So, Rosler equation. The equations are x dot is equal to minus y minus z, y dot is equal to x plus a y, and z dot is equal to b plus z x minus c. So, these are the equations. 3 variables x, y, z and 3 parameters a, b, c. Out of that, we will assume a is equal to 0.2, b is equal to 0.2, and we will vary c, okay, and we will see what happens. So, let us start with that. Let us start with this orbit. You see, it is doing various things, but ultimately converging onto a period 1 or periodic orbit, right? Can you see that? So, it has converged onto a periodic orbit. So, if all these were initial transient really. So, they are not of our concern. We are concerned with what is the steady state behavior and it is a periodic orbit. In this case, your parameter C was 1.9. Let us increase it say 2. I will make it a little larger. So, now see what has happened. It has again converged onto an orbit which is a periodic orbit. Can you see that? So, let us increase the parameter slightly, say to 3. Then if you now run it, can you see what is happening? It is actually traversing 2. I'll make it slightly less, then it will be clearer. 2.8 maybe. As it is doing so, let me now it will be easier to see. Now see what is happening. What will you call it? A period 2 orbit. So, it has 2 loops clearly, it has 2 loops. So, it is slowly converging onto that, that is why you see that as thick, but actually it is a period 2 orbit. So, if you now increase it to say 3.2, still a nice period 2 orbit. Can you see that? Okay. I would prefer to turn it further. Yeah, then it will be easier to see. Now, I will make it 3.4. I am slowly increasing the parameter in steps. It is still a period 2 orbit. Okay. It is, I do not know what, right? Something strange is happening. Let us see it from again from that angle where we started. The orbit is actually not stable. So, it is coming close to it, but then it is going away. Can you see? Here you can easily see that this orbit is you can see the plane, right? You can see the plane and you can easily figure out, okay, can we place the initial condition somewhere in the middle? This is -10, this is 15. So, here it would be something like 0 and here also it will be 0 and here it will be like -5. Let us do that. 0, 0, -5. Let us start the initial condition there and see what happens. Okay. Can you see the plane? There is a plane passing through it. So, obviously, that plane will have at the middle an equilibrium point. If you can calculate the equilibrium point from the set of equations that I have given you, you can easily determine that equilibrium point. But it is very clear from the orbit that it is definitely a complex conjugate eigenvalue case with positive real part. It is going out. It has started and then it has gone out. Okay. But then it did not really go out, something else happened. As it is going out, it is again getting thrown in. By that mechanism, it is producing this what is known as a period 4 orbit. You see. Oh, so far it was a period 2 orbit. Now see, the period 2 orbit has broken up. Now it is a period 4 orbit, right? Because this has now separated out. If I increase it further, it will be clearer. Fine. Now let us increase it to a larger value. See, you can easily see that it is spiraling out, but it is failing to go out because something happening outside that is throwing it inside. That is another mechanism by which you can have a bounded orbit. Why will very close initial conditions separate out? Because this fellow is anyway a spiraling outward orbit. Spiraling outward orbit means it will have a e to the power lambda e to the power sigma t plus sinusoidal term of omega t. That sigma t will have a positive value, which means that for one initial condition it will go in one way, the other initial condition it will also expand exponentially, and as a result their separation will go out. So, because of this expanding character, this will have that sensitive dependence on initial condition. I will clarify that further, but presently is that clear? So, let me make it clearer.
So, if we keep the parameters the same and just change the initial conditions, the plane will that plane change?
His question is, if I keep the parameters the same, but if I now change the initial condition, will the plane change? Obviously not, because the plane is given by the set of equations. So, if you solve the set of equations, you do not solve it, just find out the equilibrium point and find out the Jacobian around it and find out its eigenvalues. They are definitely not dependent on the initial condition. So, you will always get the same plane, same set of eigenvalues, so that if an initial condition is on that plane, it will behave in a certain way. But supposing you are starting from an initial condition that is away from it, what will happen? It will be determined by the other eigen direction, and here that eigen direction is such that it is pulling it in. So, pulling it in, and that is what is happening. You have the spiraling outward orbit, but that outward thing, here is a plane. That plane, normally if it is a linear system, it is just a plane, but if it is a nonlinear system, the plane associated with complex conjugate eigenvalues will bend, and that is what has happened. It is bending, and then it is throwing the orbits inwards again into that center. So, again it is spiraling out. That way it is keeping it bounded. So, these are sort of two possible mechanisms. There are more, but I will not go into each and every mechanism. What I am trying to point out is that these things are highly possible in a nonlinear system. Not only highly possible, actually these things are very prevalent in nature. And as the story goes, you see, Newton's prime contribution was to show that all the bodies in this universe at the time, in his time, people believed that the visible stars are the whole of the universe. Now we have far better look, but nevertheless, the point was that all the heavenly objects move by very deterministic laws, and the deterministic laws are exactly quantifiable. One says that any two bodies attract each other with a force G m1 m2 by r square, and the second thing is that if you have a force, then the body will move, and how will it move? Force is equal to mass into acceleration. That is a differential equation. Solve it, you get the solution, which means, and if you have an initial condition, it will move depending on the set of equation that you have. With that, it was possible to determine the trajectory of Mars, Venus, things that were completely unthinkable earlier. People earlier thought that these things are sort of move on their own, but now things were quantifiable, determinable, one could predict. So, that gave sort of a idea that everything in this world are deterministic, you can determine where it goes. There was a bit of problem, however. The problem was, okay, take into account the solar system. How would you determine the trajectory of, say, Mars? You would say that it is pulled by the sun, and therefore, there is a g m1 m2 by r square attraction to it, and the force will be exactly that, and the mass into acceleration will be equal to the force, which means it is exactly measurable, exactly determinable. You can if you measure the initial condition, you can predict how it will move, exactly which trajectory it will follow. Does it actually follow that? Now, there were a bit of complication, because when we talk about this, we are only considering the effect of the sun, not of the other planets. Yes, there could be other planets into consideration. There are 9 planets, and therefore, you have to consider all the 9 planets in their pool. With that idea, people are slowly getting the idea that in order to talk about the whole of the solar system, you actually have a n body problem with n whole numbers. Okay. But still nobody knew the solution of that kind of a problem. The question was essentially, is the solar system stable? What will happen to the solar system later? Now, it so happened then that in 1887 or so, the King of Sweden, to celebrate his own 60th birthday, he announced a prize money for somebody who can solve this problem. N body problem, Newtonian equations, n whole number, you can assume n to be 9, and then go ahead and prove that the system will be stable. Many people tried it and failed, many people tried and gave up. So, one fellow who did not give up was Poincaré, Henry Poincaré, the famous mathematician. He reduced the problem. He argued initially that, okay, forget about the 9 body problem. If I start with a 3 body problem, and if I can solve it, then we can extrapolate that solution, that logic, into 9 bodies, no problem. So, he took up 3 body problem. There are 3 bodies, say Sun, Jupiter, the biggest planet, and one other planet. Then how would I write down the equations? He proceeded a lot. He could not exactly solve it, but nevertheless, whatever he submitted, that was mathematically so very illuminating that he won the prize. And when he was preparing the talk to accept the prize, he revisited the calculation and detected an error. And when he detected an error, he wanted to recalculate and stuff like that. It is at that point he realized that all the things by which he claimed to have shown that the solar system is stable are wrong. So, there are issues that he hadn't realized before, and now it is known that essentially he stumbled upon the fact that there could be such orbits, chaotic orbits in the solar system, and something that he did not understand, and so he gave up. But that was the first inkling that something could be problematic. Now, what exactly is the problem? Notice, the problem is this: whenever I want to predict something, say I want to predict the motion of the Mars 10 years later, what do I do? Fine, I can write down the differential equations. 3 body problem, assume 3 body problem, Sun, Jupiter and Mars. The effect of the other planets are really negligible, so neglect them. So, you can write down the equations really, and then what will you do? You will measure the initial condition, you will look at it with a telescope and then say that, okay, now the position is this, and then look for some time, so that you can measure the change of the position, from there calculate the velocity. So, this is the position, this is the velocity, you can do that, and the masses are also known really. So, you can also calculate the momentum. So, the position and the momentum initially are known, differential equations are given, predict it, solve it. In those times there were difficulties because you did not have computers. So, solving large differential equation means months of effort to obtain the exact solution, but nevertheless forget about that. That was a technical problem they had. For us the matter is clear, we can solve it. But then notice that whenever you are looking at a planet and trying to find out the initial condition, it will always have some error, you can't avoid it, there will always be some error. Errors coming from the precision of your telescope, precision of your observation. So, there will always be some error. So, imagine that the position and the momentum of the planet Mars is plotted in this position momentum plane. So, position x and momentum p. In that case, say it was found to be here. Can we say with confidence that it is here? No, because mathematically you will always say it is somewhere within this error ball, right, because you know that my measurement is accurate to such an error. So, there will always be some error ball. And then how will you predict? You will say, notice that you will not say that let us predict starting from this initial condition, you will say that I have to do the prediction starting from this error ball. Wherever this ball evolves, which means all the points inside the ball evolves, the final state could be anywhere in that, clear. So, say this the ball evolves to something like this after some time. So, you will say that after this much of time, elapse of this much of time, it is somewhere within this error ball, clear. Now, it so happens that for most systems around you, this resulting ball is smaller than the initial ball. The resulting ball, that means after some time if you predict, that means you solve the differential equations starting from all initial conditions inside the ball, then you will get some object after some time. That object in volume will be smaller than the initial. That follows simply because these volumes contract. If it is a dissipative systems, these volumes in the state space contract. If it is a non-dissipative system, they will remain the same, but nevertheless the volume will remain the same, but nevertheless you can do the prediction. But now suppose you have a system that has a equilibrium point which is unstable, say it has a saddle equilibrium point, then what will happen? If it is a saddle equilibrium point, say an equilibrium point that is a saddle. So, like this. Now, if to start with an error ball around it, how will that error ball evolve? Yes, this side it will be squeezed and this side it will be elongated, and as a result of which you will find that after some time it has become like this ellipse, right. If you start ideally from a circle, it will become an ellipse. If it is a 3-dimensional system, if you start from a sphere, it will become an ellipsoid. But let us consider the 2D system first. Now, after some time what will happen? This will further increase, and finally it will become a thin elongated thing, and that is how it ultimately in a linear system it goes to infinity. Fine. In nonlinear systems also, if you have a saddle equilibrium point, then the similar thing will happen. That means it will expand to one side, it will tend to infinity, but in a chaotic system that is not allowed, because in that case it is going to infinity. You cannot allow it to go to infinity. It is always to be bounded. How can you get that bounded then? The only way you can get that bounded is if it is elongating, and after some time, say I will draw a few. So, from here it has become elongated like this. From here it will become further elongated like this, but that must be arrested. The only way it can be arrested is if it folds like this. Okay. So, this is the phenomenon that actually happens in a chaotic system. This is the phenomenon that actually happens in a chaotic system, which means imagine that you have taken a duff. Have you seen your mother making paratha? Huh? So, you take a duff and then you roll it into a big thing, and then what does she do? She folds it, right, and then again she presses it, then again she folds it, and that is why oil goes in those layers. So, you have this layered structure. So, in every iteration, what is she doing? She is making it expand in one direction, fold in the other direction, expand and fold, expand and fold, expand and fold, and that is how the paratha is made. Now, in a chaotic system, something similar to that happens, which means in the state space there is expansion. It has to happen because you have the a saddle orbit, for example. If you have a saddle equilibrium point, then there is an expanding direction, it expands. So, it expands, and but that expanding direction folds, again the whole thing expands, expanding direction folds, and that way the whole thing can be kept within limits. Notice another important thing. Another important thing is, suppose you have a system that is dissipative and you start from an initial estimate of its position like this, but an error ball like that, and then you evolve it, and suppose it becomes smaller. What does it mean in terms of the prediction? See, it means that you can predict the future, and the prediction is quite accurate. Even if there was an error in the initial estimate, after the prediction that possible error has gone down, smaller. Okay. That is the character of a stable dynamical system. If you have a stable dynamical system, it contracts in all the directions, and so prediction becomes very accurate. If on the contrary, you have a situation like this, you have this, but then that expands in some directions and goes like this. That is what I have shown. If you have a saddle equilibrium point, that is what would happen. Then what does it mean physically? Physically, it means that after this much of time, if you have estimated that it would be here, and if you make a same error ball, you would find that the future prediction has become unreliable, because it can now be anywhere within this. The future prediction has become unreliable. Why has that happened? Because two very close initial conditions are actually moving away from each other. Okay. So, in case of chaotic system, we have seen that is what happens. They move away from each other, that is the meaning of the term sensitive dependence on initial condition. But when that happens, if you have very close initial conditions moving away from each other, then since you do not know within certainty, with some certainty, whether the initial condition was actually here or here, your prediction becomes somewhat meaningless. Okay. Now, it is known that yes, the solar system is unstable, it is known, but how come it has remained like this for quite a long time? Because the time scale is quite large. In what way is it unstable? Suppose you measure the position of Pluto, and you know that if you measure it, there will always be some inaccuracy, and suppose with that distance the inaccuracy is only to the extent of 1 kilometer, highly possible, right. Having incurred an error of 1 kilometer in the distance of Pluto is a quite pardonable offense. Nobody will put some scientist in jail for that. But then it has been calculated that now with that error ball, if you allow Pluto and its state to evolve, then within something like 100,000 years, the distance of the size of the error ball will become the size of 1 astronomical unit. Do you know what 1 astronomical unit is? It is the distance between sun and the earth. So, the error will become this big, uncertainty in the prediction will become this big. So, we will not be able to predict with certainty its position at all, and the error, prediction error will be this big, the distance between sun and the earth. That is why it is said to be chaotic. The motion of the satellites of many of the major planets are also found to be in the same way chaotic. Motion of the asteroid belt, individual bodies in the asteroid belt are also found to be chaotic. So, that is one thing, that we live in a system which is itself unstable. Still we have, by the way, when I say that 100,000 years it will become so big, you felt that 100,000 years, no, it is too big, so I do not have to bother about it. 100,000 years is very small time in comparison to the time frame in the solar system. How old is the solar system? Do you know? 4.6 billion years. 4.6 into 10 to the power 9 years. 100,000 is just a moment in comparison to the age of the solar system. Fine. The whole thing was stumbled upon when finally people, I mean, Poincaré was pretty old. After that, people forgot about him. What I am telling you are all fished out of his papers pretty long, pretty much later. But then the actual inkling of the problem came when people tried to study the weather. And weather prediction is a business that scientists have been involved in for a long time. People try to predict the weather. And why does the weather change? Because there are heating on the surface of the earth, there is a cold temperature at the top, so there will be circulation. And the circulation follows partial differential equations which can be written down, you can solve it. So, there has always been the attempt to write down the partial differential equations, solve them and then predict in which part there will be a storm brewing up, in which part the pressure will go down, so that there will be some inclement weather, and all these things can be predicted. But in order to do that, what people do now is to have weather monitoring station where the humidity, the pressure, the temperature, everything is monitored, and there is a grid of such things all over the globe, and those things are related to a certain place where a supercomputer does the calculation and finally tries to predict. Now, this man Edward Lorenz in MIT was also in that business. He was trying to develop a model with which you can model of the weather with which you can predict. So, he considered a very simple system, a ground being heated up, so that you have the air going up, at top it is being cooled down. Okay. So, this is hot and this cool. So, what will happen? It will go up, it will get cold and then it will come down. So, if all the places get hot, then how does it come down? After all, it has to come down. So, he devised a model in which he considered a loop. Imagine a physical loop made by glass, and it is, say, heated by a Bunsen burner here, and here it is there is something to cool it down. Okay. So, what will happen? This part will tend to go up, this part from here it will tend to go down. So, it will establish a circulation, and you can easily write down the differential equations for that. And these differential equations initially were partial differential equations. With some approximation you can obtain ordinary differential equations from there, and that is what the Lorentz equations were, which I dealt with in the last class. And he at that time there was, the computers were pretty primitive, 1963, very primitive. So, that he would have to do the calculation, obtain the result, and at the end of the day whatever the results are, he would have to enter that as the next day's initial condition, and that would go on. So, after some time, one day he did that, he entered the results, but at the same time the computer went on calculating it. So, he found that if he enters the initial condition by hand, then it shows one prediction, and if it continues the calculation by itself, the computer does it by itself, then it shows a completely different thing. Then he realized that actually the amount of error incurred in his own hand entering of the data, that means that is within certain precision, that elimination of the last few digits or error in the last few digits is what is ultimately building up and finally making the prediction impossible. So, that was the start of the whole game of nonlinear dynamics and chaos theory. So, you can see such behavior in various types of systems. Some of the systems that you have already obtained equations of. For example, while we were doing the Lagrangian formulation, we have obtained the equation of this system, right? Double pendulum. You can take that double pendulum and simulate it. You will find that start from any arbitrary initial condition and it will go into a chaotic motion. You will see that. Okay. You have also done a pendulum with oscillating support. You have done that. Simulate that with all the tools in your hand. You have the differential equation, you have the Runge-Kutta method simulation code written up. Simulate that, you will find that you will get the same kind of behavior. Take any value of the mass and the length, whatever. Okay. But yes, ignore friction in this case. Why? Because if you have friction, after some time it will come to the vertically downward position. There will be no interesting dynamics. So, in this case at least ignore friction. In this case you may consider friction, because there is a forcing function. Okay. So, you have all these different types of systems which ultimately lead to a chaotic behavior. Now, an important thing. If you have a system like this, where you are yielding a smaller final error ball starting from a larger initial error ball, then it is predictable. If you start from a smaller error ball and it goes and beats a bigger one, it is where prediction fails. Okay. Now, if all systems in the world were like this, can you visualize such a world? What will happen? What will happen is that it is a vision that Newton started, and post Newtonian scientists took to some level. What was the idea of Newton? He said that anybody's future state can be predicted from the initial condition if I can write down the differential equations, which means that the future of anything is uniquely determined by its past. If the future of anything can be uniquely determined by past, I can also say that what I am saying now, that means my vocal cords are vibrating in a particular way to utter those words, my tongue is moving in a particular way to express my thoughts, the things inside my brain are moving in a particular way to embody that thought. All these were contained in the past in some way, so that a normal prediction with the initial condition and the differential equation will ultimately yield this lecture being delivered. So, somewhat absurd, right? The reason that you have smiled is that yes, that is absurd. So, there must be something in the nature that prevents from that from happening. In fact, that hard determinism, as it is called, that means everything can be predicted, was nicely written by Laplace, who whose name you definitely have heard. Laplace was a French mathematician. He was at the center of the French Revolution also. He was a statesman, he was everything, mathematician. In his book, he wrote that if there is some intelligent being who has the access to all the initial conditions of all the bodies in the universe, that means you know the initial state, initial position, initial momentum of all the bodies, then that intelligent being would be able to predict infinitely into the future what happens in this world. Not only that, it will be also able to, should I call predict, retrodict into the past what happened in this world. Okay. Now, that vision has been proved wrong. Why? Because the reason that you laughed, this is quite absurd, that all my tongue, my brain, my hand, my vocal cord and all these are moving in such a way. Why? Because something happened a million years, the initial conditions a million years ago determined that. No, that is not possible. So, there must be something in nature where there is a possibility of doing something which is not exactly predictable even in theory. You can see that if everything were like this, predictable, in that case that is true. Now, it so happens that we cannot predict into the future. We cannot predict in the future, not about everything. We can predict the position of the Mars, we can predict the position of the Jupiter, but then not into a million years. Why? Because that is also unstable system. And for things around us, we cannot predict even today. I cannot say where he will be tomorrow, can I? I cannot, even tomorrow. After going out of this class, where he will go, I do not know, and nobody can predict. Where will his molecules be? It is not possible to predict, even though I know his initial condition, his position, momentum, smiling, I know. So, it means that in nature there are things where the prediction does fail, and there are things where the prediction does not fail. Both types are there, and because these types are also there, you have this physical universe as we know now. Okay. That is why the occurrence of such nonlinearity is actually essential to the action of the world that we know physically. Okay, we have learnt about a few types of behaviors in nonlinear system. One, that it could be equilibrium point. Stable behaviors, it could be a stable equilibrium point. 2, limit cycle. Limit cycle could be high periodic, period 2, period n, it could be chaos. There is one fourth thing which I need to talk about before we leave the subject, that is where how should I say, in any oscillation you can always identify a frequency of oscillation, right. Now, if there are two frequencies, then what will the waveform be? Say one frequency is this, another frequency is say a few times that frequency, it will become like this, right. You can see another frequency characteristics. If you take the Fourier transform, you will see two peaks, one corresponding to this frequency, other corresponding to this frequency. Now, such systems also can happen only in nonlinear systems, such behavior. You cannot have such behavior ever in a linear system, that is typical nonlinearity, but there is a little more to it. Uh, as we have seen, we are trying to visualize everything as motion in the state space, not in the time domain. So, this is a waveform in the time domain, but a more clearer geometrically intuitive idea will appear if we try to figure out how will this orbit look in the state space. Now, in the state space, an orbit like this will be a closed loop. So, it will be a closed loop. If you, it will have a certain frequency. That frequency will determine if you start from here, after how long you come back to that same point. Now, there is another frequency with it. How will it be manifested? It will be manifested. Can you see how? It will be manifested by a motion like this. Ultimately, you can see that the system's behavior in the state space. So, it is x, y and z in the state space will be on the surface of a torus. Can you see that? It will ultimately be confined to the surface of a torus. Let me draw clearly. Say there is a torus like this, and the orbit is actually going around the torus. That is how it can have two frequencies, one frequency corresponding to the rotation in the bigger circle, another frequency corresponding to the rotation in the smaller circle and the bigger circle. There are two frequencies, f1 and f2. Now, these two frequencies could be commensurate and could also be incommensurate. What does commensurate means? One, okay, that you can define a number that is integer multiple of both. That is the concept of commensurate. You can define a number. For example, say 2 and 5. 5 is not an integer multiple of 2, but nevertheless 10 is an integer multiple of both. So, you can define a number like that. If that is so, then what will happen? Suppose you the frequency here is 2 and the frequency here is 5. 2 hertz, 5 hertz. What will happen? By the time you give 5 rounds around that, this fellow has gone many rounds, but then after 5 rounds of this, it will come to the same state, okay, which means such an orbit will be periodic. So, even if that is an orbit on a torus, it will be a periodic orbit. It will be a periodic orbit. But if these two frequencies are incommensurate, that means the time taken to go around the bigger circle and the time taken to go around the smaller circle are not, their ratio is a irrational number, then it will never come back to itself. Then it will forever go on winding around this torus, but it will never come to the same state. You can see that. So, you have the aperiodicity condition satisfied, it is still aperiodic, okay. But no, in this case there is no sensitive dependence on initial condition, because there is no moving away from each other. If you start two states very close to each other, they will forever remain close to each other. Their distance does not increase, does not decrease, they will remain the same. Such behavior is called quasi-periodicity. Which one? where the two frequencies are incommensurate, the ratio is a irrational number, then you have what is known as quasi periodicity. If the ratio is a rational number, then you have ultimately a periodic orbit, but then there is a difference between that periodic orbit and the other types of limit cycles that we have heard of so far. Why? Because there are two frequencies. If you draw the Fourier transform, you see two sharp frequencies, only there their ratio is a rational number. So, that is different from what you have in the normal periodic orbits. In order to signify that, there is a special name given to such periodic orbits, that is mode locked periodic orbit. Why mode locked? Because there are two frequencies, they are locked into a state where they are rationally related. You can easily imagine that such a system is created by a physical system in which there are parameters, and you can change the parameters the way we were changing so far. You are changing the parameters, and as you are changing, then it will the two frequencies will change. So, if say the frequency ratios will change, strangely you will find that for a large parameter range, the frequency ratio gets locked to certain range, and that is why it is called a mode locked periodic orbit. Do you know any very common example of a mode locked periodic orbit? Very common example. Earth and the moon, yes. How does the moon rotate around the earth? How many times? What is the speed of rotation? What? Okay, around 29 days. And moon is also rotating around its own axis in how long? Exactly the same. Exactly the same. Why? Could be something different? No, it is not something different, and that is exactly why you always see one face of the moon. The reason is that they rotate at exactly the same frequency. The speed at which the moon rotates around the earth, it rotates around its own axis at exactly the same speed, and that is why you always see just one face of the moon. That is an example of a mode locked periodic orbit. Here the locking ratio, frequency ratio is 1 to 1. And there are other satellites in which the ratio is 1 to 2, 1 to 3. There are satellites in the solar system like that. So, you have this kind of mode locked periodic orbits. The mechanism by which this mode locking is caused will be a bit difficult for us to deal with now. We will try to deal with later if there is time. But now that more or less completes the orbits on torus could be one quasi periodicity, and mode locked. Okay. So, these are the possibilities. So, in general, these are the new possibilities that has opened up the moment you have started to consider nonlinear systems. In the linear system, equilibrium point was there, but nothing else. All these possibilities are typical and specific to nonlinear systems. Now, for us engineers, there is another matter of concern. As I told you, whenever we engineers do something, design something, for example, we design a oscillator, would like that to be stable. Okay. And there are situations in which we want something to work in chaos. Why? Wherever, for example, we need a random number generator. Yes, physically we do. cell phones for example, they need. So, all the time in your pocket there is a chaotic system running, it has to be. So, we want those things to run like that and to run stably like that. It has to be after all a stable behavior. Chaos should also be stable in the sense that the chaotic behavior must be reliable, and wherever you want a quasi periodic behavior, a mode locked behavior, those things also should be reliable. But then if you have a linear system, its stability is trivial. How do you know understand its stability? We calculate the eigenvalues. If the eigenvalues have negative real part, it is stable. If they are positive real part, they are unstable. That is what you have learned. But that idea cannot be applicable to all these systems. That is applicable only to this. So, how do we then visualize the concept of stability of a limit cycle, concept of stability of a chaotic orbit, concept of stability of the orbit on a torus? Yes, that is what we will deal with in the next class. Okay. Thank you very much.